Hi everyone. Let's wait for a few more minutes. Okay, so let's start with this question. So a coil of wire 0.25 meter long and which is having 400 turns with current 15 ampere. We need to find the magnetic field strength as well as the flux density. Given that the coil is in the vacuum, that means permeability is only mu zero. So try to find out and put it the answer in the chat box. So anybody found the answers? Okay, let me solve it. So we have some wire which is the length is 0.25 meter and current is passing 15 ampere. So and sorry, this is a coil. So the length of the total wire is 0.25 meter. So there is some coil and the length of the wire is 0.25 meter, total length of the wire, and the turn number N is 400 and the current in this coil is 15 ampere. So for a coil, the magnetic field strength, as we know from higher secondary classes, that magnetic field strength is given by Ni by L, where N is the number of turns, I is the current. Turns number and current, this is length. This length is the length of the coil. So in this case H will be 400 into 15 by 0.25. Sorry, which will the answer will be ampere per meter. So this was the magnetic field strength. Now magnetic flux or the B. B is in general related as mu H, where mu is the permeability of the medium. In our case, it is mu 0 because it is in the coil is in the vacuum. So flux density equal to mu 0 H, and the value of mu 0 is 4 pi into 10 to the power minus 7 SI unit. So the final B will be Tesla. So this is the magnetic flux density and this is the strength. Okay, so next question. So there are three questions clubbed together. Given the magnetic flux density within a bar of some material is given as 0.63 Tesla at an H field. H field means magnetic field strength of 5 into 10 to the power 5 ampere per meter. Now we need to compute A, magnetic permeability, B, magnetic susceptibility, and C, type of magnetism that the material shows. Type of magnetism means it shows ferromagnetism, antiferromagnetism, or paramagnetism, etc. So try to solve it. So anyone?
The B value is 0.625.
D means unit.
Sorry, new value is 1.256.
New value. Okay, let me check. No, mu value is 0.126 into 10 to the power minus 5.
1.256 in 10 to the power minus 6. That means
Right,
0.1256 in 10 to the power minus 5.
right.
Yeah, chi value magnetic susceptibility, find it, sir. Once, wait,
Okay.
sir.
Yeah. So,
Magnetic susceptibility 9 ada.
uh, no, magnetic susceptibility should be pretty low actually. 0.0031, something like this. 0.0031. Okay. Let me
Second
solve
year
it.
derives.
So given that B equal to 0.63 Tesla and magnetic field strength is 5 into 10 to the power 5. So for A, we just know that B equal to mu H, mu equal to B by H. So the answer is 0.126 into 10 to the power minus 5. Then part B, we need to find the susceptibility. So mu relative permeability is given as mu 0 1 plus chi, where chi is the susceptibility. So then we can find this is not mu r, rather mu s itself. That means mu by mu 0 minus 1, and mu by mu 0 is called mu relative minus 1. So minus 1. So the answer is 0.003185. This is the chi value. And let's come to the C part. So we know whenever chi is positive, this implies either paramagnetic or ferromagnetic. If chi is negative, then it implies diamagnetic. Now for chi positive, there is two possibility, and the difference between ferromagnetism and paramagnetism is that for paramagnetism chi is pretty low, or for ferromagnetism chi is very large. So chi, the susceptibility, actually represents the how much susceptible the material is when we apply the magnetic field in terms of magnetization. So as ferromagnetics are more susceptible to the magnetization in presence of magnetic field, so the chi is large, and paramagnetic are pretty low in terms of susceptibility, but it is still positive. So from this we can say that the material is paramagnetic. So next question. So the question is compute the saturation magnetization as well as saturation magnetic flux density for iron, where the atomic weight is given and the density is also given. And another information is the magnetic moment per atom is 2.2 Bohr magneton. So mu b is basically Bohr magneton, unit of magnetic moment. So we need to find the total number of atoms per unit volume. Then we can find the magnetic moment per atom and consequently saturation magnetization. So anybody found the answers? Class. Okay, so let me solve it. So given atomic weight is 55.8 and then density rho is 7.87 gram per semi cube. These are the information. So, so to find saturation magnetization, sorry, ms will be number of atom. Sorry, Na will be confusing. It used to represent Avogadro number. So number of atom in the system times the magnetic moment per atom. Per atom, and this is number of atom. So we can easily found the number of atom in the system because we know rho Na by m gives the number of atom. Basically, yeah, because rho is n m by Na. Where m is the atomic mass, Na is the Avogadro number, and n is the total number of atoms. So rho is given as 7.87 and then Avogadro number. (55.8) and this will be in atom per semi-cube. So the total number of atom per unit volume is 0.849 into 10 to the power 23. Semi-cube. So then mu atom or the total magnetic moment. So mu is given as 2.2 mu b. This is magnetic moment per unit atom or per atom. So if we found that 2.2 into mu b is in SI unit, it will be 9.27 into 10 to the power minus 24 ampere per meter square. So this is ampere per meter square. Okay. So the saturation magnetization MS is N into mu, total mu basically. So the N we found 0.849 into 10 to the power 23 atom per semi-cube. So we need to convert it to meter cube. So 10 to the power 2 to the power cube. And then magnetic moment per atom. So this is the saturation magnetization per unit volume. So if we found the answer, it will be so the answer is 1.73 into 10 to the power 6.
731.
SI unit. So this is the saturation magnetization. Now in the question we have also asked to find the saturation magnetic flux density, but this is not possible if we are not given H, the magnetic field strength. Okay, so this we cannot calculate actually unless we are given magnetic field strength. Okay, so next question. Okay, so the question is the magnetic field intensity in a piece of magnetic material is 10 to the power 6 ampere per meter. Now, if the susceptibility of the material at room temperature is given as 1.5 into 10 to the power minus 3, so we need to compute the flux density and magnetization of the material. At the end, we also identify the type of magnetism that it shows. So let's try to find out, and then I will solve. So anybody found any of these answers? Magnetic flux or magnetization? Okay. So we are given magnetic field intensity means H equal to 10 to the power 6 ampere per meter, and susceptibility chi is 1.5 into 10 to the power minus 3. So we need to find magnetic flux density and then magnetization, then type of magnetism. So in presence of magnetization, B is actually given by mu 0 H plus M. Otherwise, if there is no magnetization, then B is simply mu H in general. So if there is magnetization, then there is an extra term of M. And nothing has been mentioned, that means we will consider that mu equal to mu 0. And how do we define magnetization? Magnetization is defined as the susceptibility chi into H. Okay. So if we write it in this way, susceptibility equal to magnetization by H, and in this form we can easily say that susceptibility is actually representing how much susceptible the material is. That means per unit magnetic field strength how much is the magnetization M. Okay, so we'll write this way: mu 0 H plus M equal to chi H, mu 0 H 1 plus chi. So then we can easily found 4 pi into 10 to the power minus 7. Then H is given as 10 to the power 10 to the power 6. 1 plus chi is 1.5 into 10 to the power minus 3. So consequently magnetic flux density comes out to be 1.257 Tesla. So this is the first part of the answer, and then we can easily found magnetization, which is chi into H. So chi is given as 1.5 into 10 to the power minus 3 into 10 to the power 6. So this will be 1500 ampere per meter. This is another part, and now finally we need to answer which type of magnetism that it shows, right? So this type of magnetism is ferromagnetism. Because the susceptibility is not very low but also not very high actually. So 1.5 into 10 to the power minus 3. First of all, this is positive, that means only paramagnetism or ferromagnetism it can be, and it is actually 0.0015. So it is not very high but not very low, so we can say it is ferromagnetism. Okay, so next question. So the question is, a paramagnetic material has body-centered cubic structure and with unit cell dimension of 0.25 nanometer. If the saturation value of the magnetization is given as 1.8 into 10 to the power 6 ampere per meter, we need to calculate average magnetization contributed per atom in Bohr magneton. Basically, this time we need to find mu given ms, saturation magnetization. So anybody have any clue how do we solve this problem? So we need to find average
I
magnetized.
think no need n value first to find out, sir, and then substitute the formula.
ms is given.
BCC structure,
Right,
n is
right.
not. A value only given, sir.
Now the saturation value of magnetization is 1.6, sorry, 1.8 into 10 to the power 6, right?
Yes, sir.
So this is magnetic saturation magnetization, or what the saturation magnetization tells us. It actually tells us magnetic moment per unit volume. So this is given 1.8 into 10 to the power 6 ampere per meter. We also given that A, or the lattice dimension, body centered cubic structure. So this A is 0.25 nanometer. So and this is
304, sir, answer.
uh, so 304 unit in units of Bohr magneton. We need to find
Yeah,
not really. Okay, so let me solve it actually.
okay, sir.
So
Value is 1.28.
okay, let me see. So magnetization is actually magnetic moment per unit volume. Okay, so given that ms is 1.8 into 10 to the power 6 ampere per meter. So this will be average or the total magnetic moment per unit volume. Okay, so what will be the volume for our system? Volume is simply a cube because it is body centered cubic cell. So 0.25 into 10 to the power minus 9 meter cube, right? This is in meter cube. So total magnetic moment mu is given as ms into v. So into 0.25 into 10 to the power minus 9 cube ampere into meter square unit, and this comes out to be 28.125 into 10 to the power minus 24 ampere meter square. So this is our total magnetic moment, and we actually need to find the answer in the Bohr magneton unit, right? So we can convert it mu in units of mu b or Bohr magneton, which will be around approximately 3 Bohr magneton. We can also write it as 3 mu b. Okay, where mu b has a value of 9.27 into 10 to the power minus 24 ampere into meter square. So this is the total magnetic moment. Now we actually need to find out, if you read the answer, average magnetization contributed per atom. So the magnetic moment per unit atom, we can find at number of atoms, right? So total magnetic moment per unit atom will be 3 mu b by number of atom in a body centered cell. So number of atom in a body centered cell is 2, right? So 1.5 into mu b. So this is the final answer. So each atom in the unit cell contributes to 1.5 of Bohr magneton. Okay, so next question. Okay, we can always have that actually. This is supposed to be not only the problem solving session, but also you can ask any doubts in any of these sessions. So let me solve this problem, and then you can ask your doubts. And just for your information, I have also filled up the form where NPTEL asked us to, if we really want to give another extra session. So I've filled up that form, which is supposed to be on the 22nd October, if the slots are free actually. So that time was also available for doubt clearing. Uh, okay, extra class 22nd October is the extra class actually. So the next week, that is 17th of October, is supposed to be the last session for me, uh, because we are supposed to give at least have 12 session. Okay, but the option is you can only take one doubt clearing session or on extra class of 1 hour or 2 hour. That was the option. So I have choose 2 hours of session on the second 22 October. So let's see what happens. If you don't have that slot free, then I'll request NPTEL guys to have any other day after, of course, 17th. Okay, but more than that, probably you will not be allowed. Okay, Nothing means we will not be allowed at least. Okay, so the next question is magnetic susceptibility of a material uh, is minus zero point 0.5 into 10 to the power minus 5. This is basically chi. And then if the material is subjected to a magnetic field of intensity, that is H is given 10 to the power 4 ampere per meter. So we need to find the magnetic moment per unit volume. So magnetic moment per unit volume we need to find, and then magnetic flux density B. Finally, we need to find the type of magnetism that it shows: ferromagnetism, paramagnetism, or diamagnetism. Okay, so we try to solve this. Meanwhile, I'll have a look at the chat box. Okay, I'll elaborate the last problem. Intrinsic magnetic flux density at 0 Kelvin for europium oxide. See, I I think so. To the best of my knowledge, there is no intrinsic magnetic flux. I mean, magnetic flux density. We have, uh,
Actually, sir, this issue is related to one question in assignment numbers 11.
okay.
It is related to one question
Mm-hmm.
in assignment 11.
Okay, so I'll have a look. Okay.
Okay.
Last question, sir. 11th question.
Okay. Okay. So meanwhile, you try to solve this problem. That's true. The magnetic material. Okay, so let me solve it. So magnetic moment per unit volume, and then B, magnetic flux density. So magnetic moment per unit volume is itself called magnetization, right? And the formula for magnetization we have seen chi h. So this will be minus 0.5 into 10 to the power minus 5 into 10 to the power 4. So M will be minus 0.05 ampere per meter square. So then we can find B. So B is given by mu 0 H plus M. H is 10 to the power 4 and then M is minus 0.05. So this is 0.01256 Tesla, and this is diamagnetic, or it shows diamagnetism as chi is negative. Okay, so previous question, okay, this question. So this is understood, right? This is just the application of formula. Okay, so what was the previous question? Okay, so we had the saturation magnetization data and then length of that unit cell. We needed to find the average magnetization, which actually means the average magnetic moment actually per atom in the Bohr magneton. So this is actually a little bit of confusion can arise there, because when we say magnetization, then it essentially says mu by V, right, per unit volume. But in this case, we have actually found that absolute magnetic moment per number of atom, means one atom contributes to how much magnetic moment basically. So if there is atom, so this contributes to 1.5 of 1.5 Bohr magneton of magnetic moment. Okay, but this is not really contribution divided by volume. Okay, so that's a bit confusing, but otherwise I am explaining that again. So let's say we have a body centered cubic material. So the overall magnetization of this material, which is magnetic moment, total magnetic moment, this is total magnetic moment. Total magnetic moment per unit volume, that means volume of this unit cell, is given as 1.8 into 10 to the power 6. Okay, and for a body centered cubic system, so what we really have, at each corner we have atoms. Atoms are not really like that, they mostly touch each other. Okay, but I am not drawing all this because it will be much more congested. And this is simple cubic, and at the center there is another atom, right? So the total number of atom per unit cell will be given by 8 atom into 1 by 8, because there are 8 corners, and each corner atom, this atom is a part of 8 unit cell, right? So plus 1, the body center. So this is 2 number of atom. So we first find out the total magnetic moment of this unit cell by multiplying the volume of the unit cell. So we got the total magnetic moment in terms of Bohr magneton. So this was our total magnetic moment in SI unit. If we divide by Bohr magneton value mu b, then we got this answer. 3 Bohr magneton is the total magnetic moment per unit cell volume. Now finally we need to find the answer, that how much each atom contributes to this value 3 mu b. So number of atom is 2, so each atom contributes to 1.5 mu b effectively. Okay, so is this clear now? Okay. Okay, regarding that oxide question, intrinsic magnetic flux. Uh, so which question? Okay, so 10th question.
Yes, sir. Question number 10.
Hmm. Intrinsic magnetic Okay, let me think. Meanwhile, we will solve any other questions.
So submission date today last 11 p.m. 11:59. लेकिन we have no idea about this question.
Okay. No, it's tomorrow actually, but okay, that's
Tomorrow
okay.
is last, sir.
Mhm. Right, right. Okay, let me solve other problems, and meanwhile, I am thinking about this. Okay, so the question is the magnetic susceptibility of three samples A, B, and C is measured as a function of their absolute temperature T, which leads to this graph. The inverse susceptibility versus temperature graph for three materials are given as follows. Now, which of these options are correct? These
I
graphs,
think option A, sir.
what?
Op-
Option A.
option, I think.
Right, right. So still we'll try to explain why this option A. Okay, so we actually need to find which of these combination is correct. So why A shows antiferromagnetism, B shows paramagnetism, and C shows ferromagnetism. Okay, let's think. Okay, so let's find out why these options are correct. So first of all, for paramagnetic, susceptibility is given as C some constant by absolute temperature. That means 1 by chi is T by C proportional to T, right? And it is exactly almost equal to T. So at T equal to 0, 1 by chi is also 0, right? So this is the case. 1 by chi becomes 0 at 0 temperature. So this is PM, paramagnetism. And then for ferromagnet, the susceptibility is given as C some constant T minus theta. So theta is the Curie temperature. 1 by chi is proportional to T minus theta. So at absolute 0, at T equal to 0 Kelvin, 1 by chi will have some negative value. Okay. So at T equal to 0, if we extend this, this will have some negative value, right? This is negative. So C shows ferromagnetism then. And then antiferromagnetism. For antiferromagnetism, it is chi equal to C by T plus Tn. and this Tn is not called the Curie temperature, rather it is nil temperature. So at before that 1 by chi is proportional to T plus Tn. That means at T equal to 0 Kelvin, 1 by chi will have some value equivalent to Tn, right? So and this 1 by right, this 1 by chi will have some positive value. So this is the case at T equal to 0. This is some positive value of 1 by k. That means A is antiferromagnet. So these are the rationale behind the correct answer of A. Okay, next question. Okay, so the next question is the unit cell side of Fe3O4 is about 0.8 nanometer and there are 8 Fe plus plus atoms, basically 2 electron has been pulled out. So 8 Fe plus plus atoms per unit cell. Now each Fe plus plus has 6 unpaired electrons, out of which 5 have spins in one direction and 1 electron has spin in opposite direction. So we need to find the net magnetic moment of each atom, Fe atom, in terms of Bohr magneton, and then we'll need to find the total magnetization of that sample Fe3O4. So if any of you found the answer, then let me know in the chat box. Okay, so let me solve. So there are 8 atoms per unit cell, right? So let's denote it by n. And so there are 6 unpaired electrons. So let's say there are 5 in the same direction and then 1 in the opposite direction, right? So that means there are 4 electrons which contributes to the magnetization. So this is actually d orbital. So net magnetic moment of each Fe atom in terms of Bohr magneton, and then finally magnetization. So Bohr magneton equal to mu b is actually E h bar by 2m, which is the magnetic moment for one electron, right? So there are 4 unpaired electrons. Sorry, there are what it says. Actually, there are 6 unpaired electrons, but out of which 5 spins have one direction, and then one has opposite direction. So there are actually 4 electrons which contributes to the magnetization. So for one atom, for one Fe plus plus atom, the net magnetic moment is 4 mu b, right? 4 Bohr magneton. So this is the net magnetic moment per unit atom. And then we need to find, this is one answer. Then we need to find the magnetization, total magnetization. So the magnetization is total magnetic moment per unit volume. So total magnetic moment will be n number of atoms, which is 8, and then each atom have 4 Bohr magneton, and then volume a cube, given a is 0.8 nanometer. So we also 9.27 into 10 to the power minus 24 ampere per meter unit. So this will come out to be 579.375 into 10 to the power 3 ampere per meter. So this is the magnetization. This is another answer. Okay. So next question. After this, I will try to solve that oxide problem, Euporian. Okay, so the next question is a paramagnetic salt has 10 to the power 28 ion per meter cube with a magnetic moment of 1 Bohr magneton per atom. So each atom contributes 1 Bohr magneton. Calculate the paramagnetic susceptibility and the magnetization produced in a uniform magnetic field of 10 to the power 6 ampere per meter when temperature is 27 degrees Celsius. Okay, so let me solve it. So what we have, number of ion is 10 to the power 28, and then each atom contributes 1 Bohr magneton per atom, and also uniform magnetic field H is given as 10 to the power 6 ampere per meter. Temperature is 27 degrees Celsius. So need to find, calculate the paramagnetic susceptibility and the magnetization. So let's first find out the magnetization. So magnetization is again total magnetic moment per unit volume, right? So this is actually N by V because this is per unit of meter cube, right? 10 to the power 28 ion per meter cube. So N by V is 10 to the power 8, and each, this is not mu b, rather this is mu. So magnetic moment per atom basically. So each ion contributes to 1 Bohr magneton of magnetic moment. So if we explicitly find it out, then 10 to the power 28 into 9.27 into 10 to the power minus 24 ampere per meter. So this will be 9.27 into 10 to the power 4 ampere per meter. This is magnetization. Okay, so is my voice breaking? So can you hear me now? Am I audible?
Yes, sir.
Okay, okay. Okay, so this is the magnetization. This is just total magnetic moment per unit volume. Then we need to find the paramagnetic susceptibility. So we know that susceptibility is magnetization per unit magnetic field strength. So this will be 9.27 into 10 to the power 4 by 10 to the power 6. So the final answer will be 0.0927. Sorry, this will be unitless susceptibility. So this is another answer. Okay. Okay, so let me try to solve the problem. So the problem says this is the problem, right? Europium oxide is ferromagnetic with Curie temperature 70 Kelvin. Given that it has J equal to 5 by 2 and G equal to 2, calculate the intrinsic magnetic flux density. Okay, so what do we mean by magnetic flux density? So magnetic flux density is this B. Okay, so we need to find intrinsic. The only thing I can remember is mu 0 H plus M. So nothing has been mentioned. So the magnetic field distance, this is applied, externally applied usually. So this will be mu 0 m, and for ferromagnetic material it can never be mu 0 actually. It is always mu, some mu 0 on plus chi, right? For ferromagnetic material chi is much greater than 1 sometimes. Okay, that information is also missing. Okay, we don't know chi, so we cannot use mu, so we need to use mu 0 only. So if we proceed in this way, now we need to find m equal to what? Okay, let me think a bit actually. So in terms of, so what essentially J, here J is actually L and S. Okay, so L is orbital magnetic moment, and S is actually spin magnetic moment of electron. So what really happens is, let's say I have some nucleus and then there is some electrons, right? So when it rotates in a circular motion or in a orbit, this also gives rise to some magnetic moment. This means the orbital motion of the electron also gives rise to some magnetic moment, which is the proxy for which is denoted by L, and S is the usual intrinsic spin magnetic moment. So each electron have can have a spin up or spin down, right? So plus mu b or minus mu b, let's say. And when there is, so we actually measure the sample magnetization or magnetic moment in the bulk. So we have some let's say material, and then there are millions of electrons, ions, etc. So for now, let's consider ions do not consider in any magnetization, okay, or magnetic moment, all coming from the electrons basically. So in electrons also, so when we measure externally, it actually captures both orbital magnetic moment and spin magnetic moment, and that effectiveness is captured by J, and it has two types of coupling, LS coupling and then another is J type coupling. So all these theories are there, but to cut the long story short, it actually gives rise to effective magnetic moment, which is approximately G into J plus 1 to the power half uh, mu B. Okay, so if we have some electrons with some J value, and G value is actually the G-man G factor, Lande G factor. it actually depends. It actually determines how much the Zeeman coupling, how much strong the Zeeman coupling is. So Zeeman coupling is another. Sorry. Another, when we apply magnetic field, electrons couples to that Zeeman field as mu dot B. So this is Zeeman energy. Okay, mu is the magnetic moment. So that is G. So in mu there is G factor. So as G increases, the coupling strength or the Zeeman coupling energy also increases. So it actually represents how strongly the electrons couples to the external magnetic field B. This is external, okay. So this is, in simple way, this is the actually effective magnetic moment. And let me apply that formula. I'm not really sure that it will work out or not. So okay, so the options are, so then mu effective will be J is 5 by 2 and 2. So 2 into 5 by 2 plus 1 to the power half. So what it will be? So this is around 3.74. So this is mu effective, and of course there is mu Bohr magneton unit. Now the volume and other information is not given, so it actually happens to be mu effective by volume, right? But volume is not given. So if we actually assume that it mu effective itself is the magnetization unit volume, basically we are assuming V is 1 SI unit, then intrinsic magnetic flux B will be mu 0 into mu effective. It actually represents M, okay. So mu 0, if we consider 4 pi into 10 to the power minus 7 SI unit, and then 3.74 into 9.27 into 10 to the power minus 24. It is not close to any of this value. Nine problem solution. Okay. Okay, so 9 problem. I hope you have understood. So this is how I will think this problem, okay? Because there are sufficient data I think is not there. So first of all, ferromagnetic substance not really will have mu 0. Some susceptibility will be definitely there. And then JG is there, that is fine. But it will come out to very small. 10 to the power minus 7 is there, and then 10 to the power minus 24 is also there. Okay, sorry, this is how I will think about this problem. But the answer is nowhere close to that. Yeah, okay. So if we have some volume, then it will reduce the value, at least power. Minus 24 will not be there. Okay, I'll think about it. And we can post any comments on the that website, right? NPTEL website. So probably there is a forum. We never use, but there is a forum. So if we can solve it, then I will definitely post it before tomorrow. Okay. So let's end the session here. So I'm disconnecting. Thank you for joining.